Binary search algorithm.
In computer science, a binary search or half-interval search algorithm finds the position of a specified input value within an array sorted by key value. For binary search, the array should be arranged in ascending or descending order. In each step, the algorithm compares the search key value with the key value of the middle element of the array. If the keys match, then a matching element has been found and its index, or position, is returned. Otherwise, if the search key is less than the middle element's key, then the algorithm repeats its action on the subarray to the left of the middle element or, if the search key is greater, on the subarray to the right. If the remaining array to be searched is empty, then the key cannot be found in the array and a special not found indication is returned. A binary search halves the number of items to check with each iteration, so locating an item, or determining its absence, takes logarithmic time. A binary search is a dichotomic divide-and-conquer search algorithm.
Overview.
Searching a sorted collection is a common task. A dictionary is a sorted list of word definitions. Given a word, one can find its definition. A telephone book is a sorted list of people's names, addresses, and telephone numbers. Knowing someone's name allows one to quickly find their telephone number and address. If the list to be searched contains more than a few items, a dozen, say, a binary search will require far fewer comparisons than a linear search, but it imposes the requirement that the list be sorted. Similarly, a hash search can be faster than a binary search but imposes still greater requirements. If the contents of the array are modified between searches, maintaining these requirements may even take more time than the searches. And if it is known that some items will be searched for much more often than others, and it can be arranged so that these items are at the start of the list, then a linear search may be the best. More generally, algorithm allows searching over argument of any monotonic function for a point, at which function reaches the arbitrary value, enclosed between minimum and maximum at the given range.
Examples.
Example, the list to be searched, L equals 1346891. The value to be found, X equals 4. This is called binary search, each iteration of 1, 4, the length of the list we are looking in gets cut in half. Therefore, the total number of iterations cannot be greater than log n.
Number guessing game.
This rather simple game begins something like I'm thinking of an integer between 40 and 60 inclusive, and to your guesses I'll respond higher, lower, or yes. As might be the case. Supposing that n is the number of possible values, here, 21, as inclusive was stated, then at most questions are required to determine the number, since each question halves the search space. Note that one less question, iteration, is required than for the general algorithm, since the number is already constrained to be within a particular range. Even if the number to guess can be arbitrarily large, in which case there is no upper bound n, the number can be found in at most steps, where k is the unknown selected number, by first finding an upper bound with one-sided binary search. For example, if the number were 11, the following sequence of guesses could be used to find it: 1, higher, 2, higher, 4, higher, 8, higher, 16, lower, 12, lower, 10, higher. Now we know that the number must be 11 because it is higher than 10 and lower than 12. One could also extend the method to include negative numbers. For example, the following guesses could be used to find 13, 0, 1, 2, 4, 8, 16, 12, 14. Now we know that the number must be 13 because it is lower than 12 and higher than 14.
Word lists.
People typically use a mixture of the binary search and interpolative search algorithms when searching a telephone book. After the initial guess, we exploit the fact that the entries are sorted and can rapidly find the required entry. For example, when searching for Smith, if Rogers and Thomas have been found, one can flip to a page about halfway between the previous guesses. If this shows Sampson, it can be concluded that Smith is somewhere between the Sampson and Thomas pages, so these can be divided.
Applications to complexity theory.
Even if we do not know a fixed range the number k falls in, we can still determine its value by asking simple yes-no questions of the form is k greater than x? For some number x. As a simple consequence of this, if you can answer the question is this integer property k greater than a given value? In some amount of time, then you can find the value of that property in the same amount of time with an added factor of. This is called a reduction, and it is because of this kind of reduction that most complexity theorists concentrate on decision problems, algorithms that produce a simple yes-no answer. For example, suppose we could answer, does this nxn matrix have permanent larger than k? In O, n2, time. Then, by using binary search, we could find the ceiling of the permanent itself in O, n2 log p, time, where p is the value of the permanent. Notice that p is not the size of the input, but the value of the output. Given a matrix whose maximum item, in absolute value, is m, p is bounded by. Hence log p equals O, and log n plus log m. A binary search could find the permanent in O, n3 log n plus n2 log m.
Algorithm. Recursive.
A straightforward implementation of binary search is recursive. The initial call uses the indices of the entire array to be searched. The procedure then calculates an index midway between the two indices, determines which of the two subarrays to search, and then does a recursive call to search that subarray. Each of the calls is tail recursive, so a compiler need not make a new stack frame for each call. The variables imin and imax are the lowest and highest inclusive indices that are searched. It is invoked with initial imin and imax values of 0 and n1 for a 0-based array of length n. The number type int shown in the code has an influence on how the midpoint calculation can be implemented correctly. With unlimited numbers, the midpoint can be calculated as imin plus imax /2. In practical programming, however, the calculation is often performed with numbers of a limited range, and then the intermediate result, imin plus imax, might overflow. With limited numbers, the midpoint can be calculated correctly as imin plus imax, imin, /2.
Iterative.
The binary search algorithm can also be expressed iteratively with two index limits that progressively narrow the search range.
Deferred detection of equality.
The above iterative and recursive versions take three paths based on the key comparison, one path for less than, one path for greater than, and one path for equality. There are two conditional branches. The path for equality is taken only when the record is finally matched, so it is rarely taken. That branch path can be moved outside the search loop in the deferred test for equality version of the algorithm. The following algorithm uses only one conditional branch per iteration. The deferred detection approach foregoes the possibility of early termination on discovery of a match, so the search will take about log 2, n, iterations. On average, a successful early termination search will not save many iterations. For large arrays that are a power of 2, the savings is about 2 iterations. Half the time, a match is found with 1 iteration left to go. 1/4 the time with 2 iterations left, 1/8 with 3 iterations, and so forth. The infinite series sum is 2. The deferred detection algorithm has the advantage that if the keys are not unique, it returns the smallest index, the starting index, of the region where elements have the search key. The early termination version would return the first match it found, and that match might be anywhere in region of equal keys.
Performance.
With each test that fails to find a match at the probed position, the search is continued with one or other of the two subintervals, each at most half the size. More precisely, if the number of items, n, is odd, then both subintervals will contain n. 1/2 elements, while if n is even then the two subintervals contain n/2, 1 and n/2 elements. If the original number of items is n, then after the first iteration there will be at most n/2 items remaining, then at most n/4 items, at most n/8 items, and so on. In the worst case, when the value is not in the list, the algorithm must continue iterating until the span has been made empty. This will have taken at most log 2, n, plus 1 iterations, where the notation denotes the floor function that rounds its argument down to an integer. This worst-case analysis is tight. For any n there exists a query that takes exactly log 2, n, plus 1 iterations. When compared to linear search, whose worst-case behavior is n iterations, we see that binary search is substantially faster as n grows large. For example, to search a list of 1 million items takes as many as 1 million iterations with linear search, but never more than 20 iterations with binary search. However, a binary search can only be performed if the list is in sorted order.
Average performance.
Log 2, n. 1 is the expected number of probes in an average successful search, and the worst case is log 2, n, just one more probe. If the list is empty, no probes at all are made. Thus binary search is a logarithmic algorithm and executes in O, log n, time. In most cases it is considerably faster than a linear search. It can be implemented using iteration, or recursion. In some languages it is more elegantly expressed recursively. However, in some C-based languages tail recursion is not eliminated and the recursive version requires more stack space. Binary search can interact poorly with the memory hierarchy, that is caching, because of its random access nature. For in-memory searching, if the span to be searched is small, a linear search may have superior performance simply because it exhibits better locality of reference. For external searching, care must be taken or each of the first several probes will lead to a disk seek. A common method is to abandon binary searching for linear searching as soon as the size of the remaining span falls below a small value such as 8 or 16 or even more in recent computers. The exact value depends entirely on the machine running the algorithm. Notice that for multiple searches with a fixed value for n, then, with the appropriate regard for integer division, the first iteration always selects the middle element at n/2, and the second always selects either n/4 or 3n/4, and so on. Thus if the array's key values are in some sort of slow storage, on a disk file, in virtual memory, not in the CPU's on-chip memory, keeping those three keys in a local array for a special preliminary search will avoid accessing widely separated memory. Escalating to 7 or 15 such values will allow further levels at not much cost in storage. On the other hand, if the searches are frequent and not separated by much other activity, the computer's various storage control features will more or less automatically promote frequently accessed elements into faster storage. When multiple binary searches are to be performed for the same key in related lists, fractional cascading can be used to speed up successive searches after the first one. Even though in theory binary search is almost always faster than linear search, in practice even on medium-sized arrays, around 100 items or less, it might be infeasible to ever use binary search. On larger arrays, it only makes sense to binary search if the number of searches is large enough, because the initial time to sort the array is comparable to many linear searches.
Variations.
There are many, and they are easily confused.
Exclusive or inclusive bounds.
The most significant differences are between the exclusive and inclusive forms of the bounds. In the exclusive bound form the span to be searched is L plus 1, 2, R. 1, and this may seem clumsy when the span to be searched could be described in the inclusive form, as L to R. Although the details differ, the two forms are equivalent as can be seen by transforming one version into the other. The inclusive bound form can be attained by replacing all appearances of L by L. 1, and R by R plus 1, then rearranging Thus, the initialization of L equals 0 becomes L 1 equals 0 or L equals 1, and R equals n plus 1 becomes R plus 1 equals n plus 1 or R equals n. So far so good, but note now that the changes to L and R are no longer simply transferring the value of P to L or R as appropriate, but now must be R plus 1 equals P or R equals P 1, and L 1 equals P or L equals P plus 1. Thus, the gain of a simpler initialization, done once, is lost by a more complex calculation, and which is done for every iteration. If that is not enough, the test for an empty span is more complex also, as compared to the simplicity of checking that the value of P is 0. Nevertheless, the inclusive bound form is found in many publications, such as Donald Knuth. The Art of Computer Programming, Volume 3, Sorting and Searching, 3rd edition. Another common variation uses inclusive bounds for the left bound, but exclusive bounds for the right bound. This is derived from the fact that the bounds in a language with zero-based arrays can be simply initialized to 0 in the size of the array, respectively. This mirrors the way array slices are represented in some programming languages.
Midpoint and width.
A different variation involves abandoning the L and R pointers and using a current position P and a width W. At each iteration, the position P is adjusted and the width W is halved. Knuth states, it is possible to do this, but only if extreme care is paid to the details.
Search domain.
There is no particular requirement that the array being searched has the bounds 1 to n. It is possible to search a specified range, elements first to last instead of 1 to n. All that is necessary is that the initialization of the bounds be L equals first 1 and R equals last plus 1, then all proceeds as before. The elements of the list are not necessarily all unique. If one searches for a value that occurs multiple times in the list, the index returned will be of the first encountered equal element, and this will not necessarily be that of the first, last, or middle element of the run of equal key elements but will depend on the positions of the values. Modifying the list even in seemingly unrelated ways such as adding elements elsewhere in the list may change the result. If the location of the first and or last equal element needs to be determined, this can be done efficiently with a variant of the binary search algorithms which perform only one inequality test per iteration. See deferred detection of equality.
Noisy search.
Several algorithms closely related to or extending binary search exist. For instance, noisy binary search solves the same class of projects as regular binary search, with the added complexity that any given test can return a false value at random. Usually, the number of such erroneous results are bounded in some way either in the form of an average error rate, or in the total number of errors allowed per element in the search space. Optimal algorithms for several classes of noisy binary search problems have been known since the late 70s, and more recently, optimal algorithms for noisy binary search in quantum computers, where several elements can be tested at the same time, have been discovered.
One-sided search.
Also called exponential search, in which you have a starting point within the array and either expect that the element you're searching for is nearby and not worth searching for from the end of the full array, or, you simply don't know an upper, lower, bound on it. Starting with a step size of 1, and doubling with each step, you look for a number greater than equals, less than equals. Once found you have an upper, lower, bound, and can proceed with a binary search. The complexity of this depends only on, and not on the size of the array.
Implementation issues.
When John Bentley assigned it as a problem in a course for professional programmers, he found that an astounding 90% failed to code a binary search correctly after several hours of working on it, and another study shows that accurate code for it is only found in 5 out of 20 textbooks. Furthermore, Bentley's own implementation of binary search, published in his 1986 book Programming Pearls, contains an error that remained undetected for over 20 years.
Arithmetic.
In a practical implementation, the variables used to represent the indices will often be of finite size, hence only capable of representing a finite range of values. For example, 32-bit unsigned integers can only hold values from 0 to 4,294,967,295. 32-bit signed integers can only hold values from -2,147,483,648 to 2,147,483,647. If the binary search algorithm is to operate on large arrays, this has two implications. The values first. 1 and last plus 1 must both be representable within the finite bounds of the chosen integer type. Therefore, continuing the 32-bit unsigned example, the largest value that last may take is plus 4,294,967,294, not plus 4,294,967,295. A problem exists even for the inclusive form of the method, as if x greater than a, 4,294,967,295, key, then on the final iteration the algorithm will attempt to store 4,294,967,296 into L and fail. Equivalent issues apply to the lower limit, where first 1 could become negative as when the first element of the array is at index 0, if the midpoint of the span is calculated as p equals L plus r slash 2, then the value, L plus r, will exceed the number range if last is greater than, for unsigned, 4,294,967,295/2 or, for signed, 2,147,483,647/2 and the search wanders toward the upper end of the search space. This can be avoided by performing the calculation as p equals r L slash 2 plus L. For example, this bug existed in Java SDK at arrays binary search from 1.2 to 5.0 and was fixed in 6.0.
Language support.
Many standard libraries provide a way to do a binary search. C provides algorithm function bzich in its standard library. C++ SSTL provides algorithm functions binary search, lower bound and upper bound. Java offers a set of overloaded binary search static methods in the classes arrays and collections in the standard Java util package for performing binary searches on Java arrays and on lists, respectively. They must be arrays of primitives, or the arrays or lists must be of a type that implements the comparable interface, or we must specify a custom comparator object. Microsoft's ANET Framework 2.0 offers static generic versions of the binary search algorithm in its collection base classes. An example would be system arrays method binary search list and greater than t-array, t-value. Python provides the bisect module. COBOL can perform binary search on internal tables using the search all statement. Perl can perform a generic binary search using the CPAN module search binary. Go's sort standard library package contains functions search, searchints, searchfloat64s, and search strings, which implement general binary search, as well as specific implementations for searching slices of integers, floating point numbers, and strings, respectively. For Objective-C, the COCO framework provides the array index of object in sorted range options using comparator method in Mac OS X 10.6+. Apple's Core Foundation C framework also contains a CVArray bzich values function.